In this video, we're going to talk about intermolecular forces. Intermolecular forces are the forces between molecules. So we talk about bonds, which are the forces within molecules. But there are also forces that exist between molecules in a substance. So we're going to talk in this video about those forces that occur between molecules. To talk about intermolecular forces, we first have to talk about a few things about molecules themselves. So if we look at a molecule, for example, something like chloromethane, which is CH3Cl, the bonds between carbon and hydrogen, if we think back to electronegativity, there's not much of a difference in electronegativity between carbon and hydrogen. You might think there would be since they're further apart on the periodic table, but if we look at electronegativity values, the difference between carbon and hydrogen is not actually that much. So that bond between carbon and hydrogen is actually considered nonpolar, all three of these bonds. However, the bond between carbon and chlorine, there is an electronegativity difference. And when we have a difference in electronegativities, we get what we call a bond dipole. So a bond dipole is when we have a polar bond where the electrons are being pulled more strongly towards one end of the bond than they are towards the other end of the bond. So in the CCl bond, the electrons are being pulled towards chlorine, since chlorine is much more electronegative than carbon. So we end up with a dipole going towards the chlorine and the electrons being pulled away from the carbon. So we would refer to this, the electrons being pulled towards chlorine away from carbon, as a bond dipole, and we would refer to this bond as a polar bond. If we have a molecule like carbon dioxide, oxygen is more electronegative than carbon, which makes each one of these bonds polar. But if we think about the molecular geometry of carbon dioxide is linear because these oxygens want to be as far apart as possible. So what happens is that these bond dipoles here go in exactly the opposite direction. Since they go in exactly the opposite direction, they essentially cancel each other out, and the molecule overall becomes nonpolar. Something very similar happens with tetrachloromethane. Tetrachloromethane is CCl4, which means that we've got 4 chlorines. So if we draw this molecule out, it's tetrahedral. Well, in each of these cases, chlorine is more electronegative than carbon, which means that the electrons are going to get pulled towards the chlorines. But what happens is, it's being pulled in equal and opposite directions. It's being pulled in 4 directions that are all away from the carbon, and they're all opposite each other. So this molecule overall becomes nonpolar. If we have something like ammonia, if we look at the NH bond, nitrogen is more electronegative than hydrogen, which means that all the electrons are going to get pulled towards nitrogen. So there's a net dipole that goes upwards, that goes up towards the nitrogen. The same thing that happens with oxygen. Oxygen is more electronegative than hydrogen. All the electrons therefore get pulled towards oxygen. So if we take the net dipole, it's going towards the oxygen. So in these cases, the bond polarities don't cancel each other out. So overall, the molecule itself would be polar. So So those molecules that are polar and nonpolar are going to become important as we talk about different types of intermolecular forces. So as I mentioned at the beginning, intermolecular forces are forces between molecules. So these are not the same thing as bonds. Bonds are intramolecular forces, meaning that they are within a molecule. Intermolecular forces are forces between different molecules. So these forces are due to the attraction between opposite charges. When we have these bond dipoles and these polar molecules, we end up with molecules that have a net or bond dipoles where there's a net negative charge on one end and a net positive charge on the other end. Those net positive and negative charges, when they're opposite, such as a positive and a negative, are attracted to each other, just like the north and south ends of a magnet. If you put the north and south ends of a magnet together, they're attracted to each other, and the magnets will stick. But if you put the two norths together, or the two souths together, they won't stick. Same thing happens with intermolecular forces. When they line up so that you have a net positive on one side and a net negative that's directly opposite of it, they will be attracted to each other. So there's 4 different types of intermolecular forces that we're going to talk about. One is ion dipole forces, and this one is separate from the other 3 because this involves ionic compounds. So it involves one compound that is ionic and one compound that is covalent. You have to have at least one ionic compound for ion dipole forces to exist in a substance. The other 3 forces we're going to talk about, London dispersion forces, dipole-dipole forces, and hydrogen bonds, occur only in covalent substances, or sometimes we call those molecular substances. So these 3 will all be present when we don't have any ionic compounds. So to give you kind of a little bit of an overview of intramolecular forces versus intermolecular forces. So intramolecular forces are what we more frequently refer to as bonds, whereas intermolecular forces are between molecules. So for example, if we think about something like hydrochloric acid, chlorine is much more electronegative than hydrogen is, which means that we're going to have a partial negative on chlorine and a partial positive on hydrogen. And the same thing on any hydrochloric acid molecule. So within a hydrochloric acid molecule, we have a bond between the chlorine and the hydrogen where they're sharing their electrons. That intramolecular force, or that bond, is going to be a very strong force. An intermolecular force is just an electrical attraction between the positive end of this hydrogen on the hydrochloric acid and the negative end of the chlorine. So this electrical attraction between the hydrogen and the chlorine, the hydrogen of one molecule and the chlorine of another molecule, is an intermolecular force but that's weak in comparison to a bond. So intermolecular forces, while they are important and they do influence the nature of matter, they are nowhere near as strong as an intramolecular force. So we're going to start off talking about ion dipole forces, since this is the only one that involves an ionic compound. So an ion dipole force results when we have an ionic compound, and if our ionic compound is soluble, it's going to break apart into its positive ions and its negative ions. If you put an ion into a substance that is polar, what's going to happen is the positive ends of the polar molecule are going to be attracted to the negative ions, and the negative end of the polar molecule is going to be attracted to the positive ions. So, for example, if this was something like sodium chloride, our sodium ions would be our positive ions. And if this is something like sodium chloride in water, the negative end would be our oxygen. So the negative end of our water molecules are going to be attracted to our sodium ions. And the positive end, the hydrogen end of our water, is going to be attracted to our chlorine ions. So what happens when you have something like sodium chloride in water, and you have all of the oxygen ends of the molecule surrounding sodium, it's not just one molecule of water that this happens with. As many molecules of water as you can fit around that sodium ion, they're going to be clustered around that sodium ion. And the same thing happens with the positive ends of the water molecule clustering around the chlorine ions. So we get this sphere of hydration around both the sodium and the chlorine ions, where water molecules cluster around these ions and surround it with an aqueous solution. So let's talk about intermolecular forces and covalent compounds. And we're going to start with the weakest intermolecular force, which is London dispersion forces. So London dispersion forces occur in non-polar molecules. And the way that London dispersion forces happen is that we get a temporary dipole in the molecule that causes an attraction between the opposite ends of the dipole. So this can happen a couple of different ways. Sometimes it's just a momentary shift in the electron distribution. The electrons are moving around the atoms, and momentarily they shift so that more of the electrons are on one end of the molecule and we have a negative end, and then, of course, the other end has a partial positive because of that. If one molecule does that, it can influence another molecule that's near them, and then we get a net negative and a net positive and so forth. And the partial positive is going to be attracted to partial negative. Sometimes that's due to what we call an induced dipole that we're going to talk more about later. And an induced dipole is when we have something that has a negative charge or a positive charge and it gets close to one of these molecules. So if a negative charge gets close to the end of one of these molecules, it may cause the electrons to shift, and it would shift away from the negative charge, so this end would become partially positive, and this end would become partially negative. Or we could have a positive molecule, a positive ion, come towards this end and end up with a partial negative and a partial positive. So the charged molecule induces that dipole, and then we end up with a temporary dipole. But as soon as that charged substance leaves, that dipole is going to go away. So these are just temporary dipoles. They're very weak intermolecular forces, but they do still influence the properties of a molecule that is nonpolar, of a substance that's made up of nonpolar molecules. So this is what I was talking about with the induced dipole. If we put something in this nonpolar substance, and the substance that has nonpolar molecules, so this is an illustration of what I was talking about with the induced dipole. If we put something that is charged into a substance made up of nonpolar molecules, we will induce a separation of charge and cause a momentary uneven distribution that gives us those partial positive and partial negative charges. So when you're dealing with a nonpolar molecule, what is it that makes a molecule polarizable? Well, polarizability is defined as the ease to which an electron cloud in a molecule, an ion, an atom can be distorted and cause a temporary dipole. So we're going to talk about the things that determine how easily we can distort an electron cloud, meaning how easily can we polarize something. So some of the factors that affect how easily we can polarize a nonpolar molecule. One of them is the size of the atom of the molecule. Something that's larger, that has more of an electron cloud, and has more surface area for an electron cloud, is going to be more polarizable. Something that's smaller, there's not as much room for the electron cloud to spread out, and there's not as much of an electron cloud to start with, because smaller molecules would have fewer atoms, which means they're going to have fewer electrons from those molecules. So as we get to larger molecules and larger electron clouds, we can distort that electron cloud easier. Another thing that affects how polarizable a nonpolar molecule is the shape of the molecule. If we've got an increased surface area, we've got increased interaction between molecules. So if we have more interaction, it's going to be easier to distort the electron cloud. So if it's easier to distort the electron cloud, then we can more easily cause a dipole. Something that's linear is going to have a higher surface area, which means that we can fairly easily distort its electron cloud. Whereas something that's branched, there's not as many places that we can get a molecule close enough to cause a distortion. We really can only get to these carbon-hydrogen bonds that are on the ends of the molecule and not really to the ones on the center. Whereas even the ones in the center on this linear molecule here are right at the surface. So it's going to be much easier to distort the electron cloud for this linear molecule than it is for a branched molecule. So if we look at molecules in terms of size, if we look at something like fluorine, chlorine, bromine, iodine, so we go down the halogens, and we go up in terms of size, what we find is as we increase the molar mass, we increase the boiling point. Boiling point is very much affected by intermolecular forces, because the stronger the intermolecular force, the the harder it is, or the more force, the more energy is required to overcome the intermolecular force. So the boiling point is going to be higher. Okay, so hopefully you can read that. So the stronger the intermolecular force is, the more energy we're going to have to put in to overcome that intermolecular force. And the more energy we're going to have to put in, the higher the boiling point is going to be. So another example of a larger molecule, if we go up the number of carbons in a hydrocarbon, so we go from butane, which is 4 carbons, to pentane, which is 5 carbons, to hexane, which is 6, heptane is 7, octane is 8. You can see we're increasing the molar mass here. We're also increasing the boiling point. If we look at the effective shape, if we look at a linear molecule here, so if we look at pentane, for example, which is linear, the boiling point is 309 Kelvin. Look at what happens when we add just one branch. So we've still got 5 carbons, but there's one branched off instead of being part of the chain. We drop to 301 Kelvin, so not too much of a drop yet. But then look at what happens when we go to dimethylpropane. So dimethylpropane, if we count the carbons, still has 5 carbons. But 3 of them are in the chain, and then we get 2 that are branched off. Look at the drop in the boiling point here. We've now got a boiling point of 282 Kelvin. So we've dropped almost 30 degrees from our original boiling point, and even 20 degrees from this boiling point. So we're not taking as much energy to overcome the intermolecular forces as we branch out here. So the next intermolecular force that's a little bit stronger than London dispersion forces is dipole-dipole intermolecular forces. So the dipole-dipole interaction occurs in polar molecules. It's an attractive force between the partial negative end of one polar molecule and the partial positive end of another polar molecule. So to be clear here, London dispersion forces only occur in nonpolar molecules. Dipole-dipole forces occur in polar molecules. So to put this in perspective, comparing it to bonds, dipole-dipole forces are about 1% as strong as a covalent or an ionic bond. And the strength of a dipole-dipole force decreases as we increase the distance between the dipoles. So if we have these dipoles really close together, then they will have a strong attraction. But as we move them further apart, then the strength of that attraction decreases. Now, a more specific type of dipole-dipole bond is a hydrogen bond. And a hydrogen bond is actually the strongest dipole-dipole interaction. However, a hydrogen bond only occurs in very specific circumstances. It only occurs when we have a hydrogen atom that's bound to a small, highly electronegative atom. And the 3 small, highly electronegative atoms that contribute to hydrogen bonds are fluorine, oxygen, and nitrogen. Those are the only possible elements that can be bonded to hydrogen that give us a hydrogen bonding: fluorine, oxygen, or nitrogen. So what happens is, remember that hydrogen bonds, and make sure you keep this in mind, hydrogen bonds are intermolecular forces. They are not bonds within molecules. So we call them bonds, but they're not really bonds. They're really intermolecular forces. Hydrogen bonding is an intermolecular force. So the hydrogen bond occurs between the fluorine of one molecule and the hydrogen of another, or between the oxygen of one molecule and the hydrogen of another molecule, or between the nitrogen of one molecule and the hydrogen of another molecule. So it's always between the fluorine, oxygen, or nitrogen of one molecule and the hydrogen of another. They're between molecules, not within molecules. So one example of this is hydrogen bonding in water. So if you have water molecules, you have the oxygen end with its partial negative and the hydrogen ends with their partial positive. We form a hydrogen bond between the oxygen and the hydrogen. This hydrogen bonding in water is actually responsible for a lot of the properties of water. It's why water has such a high surface tension. It's why solid ice is actually less dense than liquid water, because what happens is that when water freezes, it orients itself so that the hydrogens and oxygens line up and form hydrogen bonds. So you actually get a molecule with a substance where there's space in here for these oxygens and hydrogens to line up, which results in open space there, which in turn makes water less solid ice less dense than liquid water. It also is a reason why water expands when it freezes, because again those molecules are orienting themselves so that the hydrogen and oxygens line up, and to orient themselves that way it ends up taking up more space overall. So if you look at the boiling points of substances that have hydrogen bonding, things like water, hydrofluoric acid, ammonia, they're all increased compared to other substances in their group. So for example, if you look at water is in group 16. So if we go down on that column and we look at hydrogen bound to sulfur and selenium and tellurium, then what we find is water has a much higher boiling point compared to the others. The same thing happens with hydrofluoric acid. If we then look at hydrogen bound to chlorine, bromine, and iodine, or ammonia bound to, compared to hydrogen bound to phosphorus, or arsenic, or any of the other elements in that column. Hydrogen bonding is a stronger intermolecular force compared to the dipole-dipole forces that would be in other molecules. So increased or stronger intermolecular forces results in an increased boiling point. So let's take a look at an example where we have to put things in order of boiling point. So we have CH3OH, CH3, CH2, CH2, CH3, and CH3, CH2O, CH3. Well, the key to looking at this is one of the points I've made a couple of times so far, is that the stronger the intermolecular forces are, the higher the boiling point is going to be. So if we look at CH3OH, we have an oxygen that's directly bound to a hydrogen. So this molecule is going to exhibit hydrogen bonding. And I'm going to abbreviate that. Then we have CH3, CH2, CH2, CH3. So carbon and hydrogen are, there's not much difference in their electronegativities. So overall, this molecule is going to be nonpolar. Now, out of the three intermolecular forces we talked about in covalent compounds, only one of them occurs in molecules that are nonpolar. And that would be London dispersion forces, which I'm going to abbreviate here as LDF. The last molecule here has CH3CH2OCH3. So if I drew this molecule out, what it would look like is, I'm not going to draw the whole thing out. And actually, let me go ahead and just draw the So what you should notice if you look at the drawing is that the oxygen is not directly bound to hydrogen, which means that we're not going to have hydrogen bonding in this molecule. But oxygen is more polar than the carbons or hydrogens. Sorry, it's more electronegative, which is going to make this a polar molecule, which means that we're going to have dipole-dipole forces. So London dispersion is the weakest intermolecular force, and it's going to be the easiest to overcome, which means that CH3, CH2, CH2, CH3 is going to be the lowest boiling point, followed by CH3, CH2, OCH3, and then finally followed by CH3, OH, which has hydrogen bonding. So as we increase the strength of the intermolecular forces, then we increase the boiling point. So to give you a couple of other examples of how hydrogen bonding is important, hydrogen bonding is actually important even in your DNA. The way that the different bases in DNA, and if you might have heard this in biology, so adenine bonds with thymine, and guanine bonds with cytosine. So the way that these bases bind in your DNA is through hydrogen bonding. Adenine and thymine form 2 hydrogen bonds. Guanine and cytosine form 3 hydrogen bonds. So we mentioned earlier sometimes we can induce dipoles. So here's a couple of examples for you on induced dipoles. If we put something like water close to a molecule of O2, we induce a dipole. So if the oxygen end of the water is close to one of the ends of O2, then we get a partial positive on one end of O2 and a partial negative on the other end of O2. So we induce that dipole there. So this chart here shows you a comparison of the strengths of intermolecular forces. So as we mentioned, London dispersion is the weakest force. Then something where we have an induced dipole, if we have something like oxygen dissolved in water, that's a little bit stronger than your London dispersion forces where we just have a momentary shift. So we get slightly stronger here. Then dipole-dipole forces. Hydrogen bonding is the strongest of the bonds that occurs in covalent forces. And ion dipole forces are the strongest, but we really only deal with those when we have ionic compounds. Okay, so this puts that in table form. So London dispersion is our weakest. That occurs between all molecules, but nonpolar molecules can only have London dispersion forces. Then we have dipole-dipole, which is slightly stronger, and then hydrogen bonding, which only occurs with molecules that have oxygen, nitrogen, or fluorine. And then, of course, we have ion dipole forces when we have ions. So intermolecular forces also influence solubility. So solubility depends on the strength of the solute-solvent interactions compared to the strength of the interactions between the solute molecules or between the solvent molecules. So things that are ionic or polar will be soluble in polar solvents. Non-polar solutes are only soluble in non-polar solvents. So we call that rule like dissolves like. Something that is non-polar is not going to dissolve with something that's polar and vice versa. They have to be similar in their polarities. For example, if we take something like water and methanol both exhibit hydrogen bonding. So those two will mix and you won't be able to tell the difference where the water stops and methanol starts because they're all mixed together. Whereas if you mix something like water and an oil or a hydrocarbon like octane is all non-polar, water is all polar, so you get two separate layers. Sometimes we have large molecules where you actually have ends that almost act as if they were different molecules. So, for example, if we have something like octanol, this is a very long molecule. So this end where we have the OHs acts as if it's polar, and that end is polar. But this end is so long that it's not as influenced by the properties of this end of the molecule. So we end up with the end of the chain that is nonpolar. And we can actually use these properties in things like soap. We have one end that's polar that bonds with the water, or that is attracted to the water, and then we have one end that's nonpolar that's attracted to things like dirt and grease that might be on your hands if you're trying to wash your hands, or grease that's on a dish if you're trying to wash your dishes. And we can use that property to dissolve grease and dirt and things like that. So we call the end that's polar that likes water hydrophilic. So hydrophilic literally means water-loving. So it's attracted to the water molecules, and it's very soluble in water. We call the other end hydrophobic, which actually literally means water-fearing. So it repels water. It's not going to be insoluble in water, but it's going to be insoluble in nonpolar molecules like grease. So I mentioned earlier hydrogen bonding in water affects some of the properties of water. So we get surface tension, which is the energy that's needed to separate water molecules, or separate molecules at the surface of a liquid. Because water has such strong intermolecular forces, it has those hydrogen bonds, we get a very high surface tension. And as we increase surface tension, we increase the intermolecular forces, we increase the surface tension. And we also increase viscosity, which is how thick a substance is. So that's how you get things like bugs that can walk on water. It's because they're light enough that they don't put enough force on the surface of the water to sink below the water. Or if you have something like a pen that's very lightweight, it will float because it doesn't have enough mass to break the surface tension of water. So we will stop here and we will get some practice with looking at intermolecular forces and determining what intermolecular forces would exist in a molecule in class. So I will see you in class.